So, in last class we have discussed about a model checking algorithm, okay, and what is this model checking algorithm? Basically, we have seen it some sort of labeling algorithm. We are going to take the Kripke structure, we will take the CTL formula, and after that we will run our labeling algorithm to label each and every state with the formula which are true in this particular state. So, basically that is why we are saying that we are going to give a model M and a CTL formula phi. So, model checking algorithm provides all state of model M which satisfy phi. So, it is some sort of your labeling algorithm. So, what basically we have in this particular labeling algorithm, the input to this particular algorithm is your model M, which is having set of state as the transition relation and the labeling function. So, already we have discussed all those issues in our Kripke structure, and along with that we are giving a formula phi, and we will check whether this formula phi is true in this model, and basically it is going to give me the set of states of M which satisfies phi. So, it is going to return a set of state where it is true. So, in last class we have seen three algorithms basically for Ex, Af and Eu. Ex is basically Ex phi, that means where there exists a part in next state phi holds, Af phi in all phi in future phi holds, and E phi until psi. There exists a part such that phi remains true until psi becomes true. And we have seen that these three are the adequate set of temporal operators by which we can derive the other CTL operators, because we are having 4 temporal operators along with that 2 part quantifier, altogether we are going to get 8 different combinations. But this is the adequate set of operators. So, if you know the procedure for these 3 operators, then we can look for the truthness of any other CTL operators. Now, in last class we have seen the algorithm, and these algorithm are some sort of your graph traversal algorithm. So, we are going to take the Kripke structure with your set of states, all the transitions, and along with that labeling function. Now, in all those procedure, what happens, we are going to traverse the entire state space, entire graph, and going to check whether the property is true in a particular state or not. So, in complexity issue, we have seen that this it depends on the length of the formula. So, what is the length of the formula? Then it is, because in each and every state we have to look for it. This is your number of nodes in this particular graph, and along with that P plus E. So, this is basically the total state space, because you have to traverse in one situation each transition. So, the complexity is turned up to be your order of your length of the formula and number of nodes and your total state space. So, it is linear in the length of the formula and quadratic in the number of nodes that we have in this process. And we have seen that we have got an well defined algorithm for this operator. So, that means we can say that we are having an automated process for CTL model checking, and this is the beauty of CTL model checking. So, we are getting a well defined algorithm and it runs on linear time. Okay. Now, we will see the use of this algorithm with the help of example. So, here in today's lecture I am going to discuss some examples only, and if time permits then we will see some of the issues also. We also said that in one of our class we have discussed about the modeling of our mutual exclusion protocol and going to check for the properties that need to be satisfied that particular model. Okay. We have considered model of 2 process P 1 and P 2, and we have seen the state space that it is turned up to be something like that we have presented over here. Already we have discussed this particular example in details. So, these are the reachable states that we have in our examples. Now, we are going to check whether the safety properties satisfied or not in this particular model. Okay. So, what is the safety properties? We are going to say that in all part globally north of C 1 and C 2. That means, at any point of time both the process should not enter into the critical section. So, both of C 1 and C 2 need not be true simultaneously. Okay. So, this is C 1 is basically says that process P 1 is in your critical section, and C 2 says that process P 2 is in your critical section. So, now my property safety property in CTL is AG north of C 1 and C 2. Okay. So, basically this is the thing that now we are having in our hand. This is the model or crypto structure that we have, and this is the formula that we are going to check whether in which other step this formula is true. Okay. So, here since it is a crypto structure, we are having the labeling of those particular atomic proposition in each and every step. Like that simple example, I can say that N1 P1, it means that the process P1 is in a non-critical section and process P2 is trying to enter into the critical section. So, that is why I am saying that the atomic position N1 and T2 are true in this particular stage, and all other states are this, and all other proposition like N2, T1, C1 and C2 are false in this particular state. Now, if you say this is a very small system, and by inspecting itself we can say that in none of the states that not of C1 and C2 is true. Okay. But still, if we are going for a bigger system, by inspecting we cannot do it, we have to apply our algorithm. So, for this small example we will apply our algorithm. Now, let us see what will happen. Now, we have seen that we are going to look into the adequate set of operators, and we say that these are the three operators that you need: EX, AF and AU, and we have already discussed the algorithm for these three operators. So, whatever CTL formula we are giving, somehow we have to convert it to these three operators. So, already we have seen the equivalence about your CTL formulas, and we know that AG can be expressed with the help of EF. So, AG not of C1 and C2 is equivalent to not of EF, C1 and C2, and these features can be again, because we have EF, but we are having procedure for AF, but we are having procedure for EU. So, this EF can be written as E true until C1 and C2, because these are the two equivalents that we have in our hands. So, I have used these two equivalents, AGP is equal to not of EF not of P, and EFP is equal to E true until P. So, I have used these two equivalents, and with the help of this equivalent I have converted this given CTL formula, and now you just see that we are having this particular conjunct, we have this E until and we have this negation. Okay. So, we have the procedure for this E until. So, we are going to use this particular E until to check whether this property holds in some states or not. Okay. Now, by looking into this particular final formula, what are the sub formulas that we are having? C1 and C2 are two atomic propositions. So, they are CTL formulas. Since C1 and C2 are CTL formula, C1 and C2 is also a CTL formula. Now, E true until C1 and C2, since C1 and C2 is a CTL formula, true is also a CTL formula. So, E true until C1 C2 is also a CTL formula. Since E true until C1 C2 is a CTL formula, so negation of this formula is also a CTL formula. So, this is the formula that we are going to look into it. But to check for this particular formula, we have to look for this particular sub formula. Once we have the labeling of this particular sub formulas, then only we can talk about this particular given formula. So, we will look for the atomic one C1 C2, then C1 and C2, then this particular E true until C1 and C2. So, now say we are having the labeling function, we will label each and every state with the help of atomic propositions. So, with the from this particular labeling function, we will get that the C1, that atomic proposition C1 is true in your set S3 and S6. So, in S3 C1 is true and S6 C1 is true. Similarly, for C2 it is true in S5 and S7. So, this is the C2, it is S5 is labeled with C2 and your S7 is labeled with C2. So, the set of states where C2 is true is your S5 and S7. So, we know the labeling of these two sub formulas C1 and C2. Once we know the labeling of this C1 and C2, then we can look for the labeling of C1 and C2. And what is the states where C1 and C2 is true? This is nothing but the intersection of these two particular sets. If we look into the intersection of these two particular states, then we are going to get a null state. So, in none of the states that C1 and C2 is true. Now, what is our next formula? This is your E true until C1 and C2. Okay. In this case also, now it is very simple, we are going to get the null set, because C1 and C2 is null. Okay. So, in the first case we are not getting any state. So, if we are getting some state, then what will happen? We are going to traverse the graph. Since the initial set itself null, so there is no point of traversing the graph. So, eventually we are going to get that E true until C 1 and C 2 is also a null set. Okay. Now, when E 1 until T 2 is a null set, then what is the negation of these things? Negation of these things is nothing but complete state space minus where the formula phi is true. So, this is basically these sets give me the where the formula not of phi is true. Okay. So, my total state space is given over here. So, my this particular the formula where this particular the states where this particular formula is true is given as your empty set or null set. So, for negation of this formula will be true in all the states. Okay. So, that means what we are saying that this is the formula A g naught of C 1 and C 2, which is equivalent to naught of E true until C 1 and C 2. So, we have seen that in all the states this naught of E true until C 1 is true. That means, we can say that in all states all path globally naught of C 1 and C 2 is true. So, from here we can conclude that the safety property has been satisfied by my model. Okay. So, this is the way that we can check. This is a very simple example. Now, we will see another example. Okay. In second example, we are saying that again we are going to apply the model checking algorithm to level the states with the formula all path globally T 1 implies there in all path in future C 1s. Okay. So, this is the property that we call as your liveness property. So, what we are saying that if any process wants to enter into the critical section, that process eventually must get the chance to enter into the critical section. This is the liveness property. Now, we are going to check whether this particular liveness property is true in my model or not. Okay. Now, again you see that we are having method for E x, A f and E u. So, somehow we have to express this particular formula in terms of these three formulas. Okay. Now, A f we are having. So, we have a process or procedure to check for this particular formula A f C 1, but we do not have method for particular A g. So, that is why we need to use some equivalent. So, that we are going to have a method or process from this particular set. Now, again similarly say A g p is equivalent to naught of E f naught of p, this is equivalent, and the second equivalent is E f p is equal to E true until p. So, we are again going to use these two equivalents. So, eventually this given formula A g T 1 implies A f C 1 is turned up to be this particular formula. Naught of there exists true until naught of T 1 implies A f C 1. So, this is the formula. Now, we have process for A f C 1, we have process for E until. So, these are the E until and this is the A f. So, we can use our model checking algorithm to check this particular formula. So, now, when we are converting this particular given formula A g T 1 implies A f C 1 and this is the equivalent formula that we are getting, and now we are concerned about this particular formula. Now, what are the sub formulas is this particular formula? Now, I can list it. Say T 1 is a sub formula, C 1 is a sub formula. Since C 1 is a sub formula, then A f C 1 is also a sub formula. Since T 1 and A f C 1 is also sub formula, so T 1 implies A f C 1 will also be a sub formula or CTL sub formula. Since this one is CTL sub formula, negation of this given CTL formula is again a CTL formula. So, we are going to get one sub formula. So, from that now since both the components true is always a CTL formula, true until we are having this as a CTL formula. So, we are going to consider this as another sub formula, and this is the final formula negation of this particular step. So, when we are going to look for the true values of this particular given formula, we must know the true values of all those particular sub formulas. We know the set of states where these sub formulas are true or the states where these are satisfied. Okay. Now, we are going to see these things. Now, the sub formula we have T 1 and C 1, which are your basically atomic proposition. So, by looking into this particular state space, we will say that T 1 is true in the set S 1, S 4 and S 7. So, this is the state S 1, S 4 and S 7. In these three particular states, the atomic proposition T 1 is true. Similarly, the set of states where C2 is true, this is your S3, C1 is true in S3 and S6. So, this is S3 and S6. In these two states, the atomic proportion C1 is true, in none of the states C1 and C2 is true. So, we are getting these two states where formula T1 and C1 is true. Now, next sub formula is your AFC1. We know the set of states where T1 and C1 is true. Now, we will look for AFC1. So, what is the procedure for AFC1? So, for any temporal operator, for this procedure we are having two steps. First step is says that if any state S is labeled with C1, then label it with AFC1. That means, wherever C1 is true, AFC1 is also true, because it is coming from our semantics of our futures, because future includes the present scenario. After that, we are going to repeat this process, label any state with AFC1 if all successor states are labeled with AFC1 until there is no change. So, we are going to repeat these things. Now, once wherever C1 is true, we are going to say that AFC1 is true and we will repeat it. Now, since C1 is true in your S3 and S6. So, AFC1 is also true S3 plus S6. Now, this is the base case that we are having. Now, we are going to enter into the loop. Now, from these two states, we are going to traverse the graph in backward direction. We will see what is the predecessor of these particular states. Okay. Now, since the predecessor is your S1, now we will see whether it is having two next state S3 and S4. Now, S3 is labeled with your AFC1 in our base case, but your S4 is not labeled with C1. So, S1 both the successors are not labeled with your AFC1. So, that one S1 will not include in this particular case. Since S1 is not included over there, so there is no sense of this particular set. So, we will terminate the loop. That means, AFC1 is true in these two states S3 and S6. Now, the next formula we are getting T1 implies AFC1. Now, when we are coming to this particular sub formula, we know the labeling of these three sub formula T1, C1 and AFC1. Now, again in this particular set that T1 implies AFC1 is equivalent to not of T1 or AFC1. So, this is simple your logical connective. So, in every state we can check it, we need not to go for a loop. So, now we are going to check where T1 is false. We know that T1 is true in your S1, S4 and S7. So, not of T1 will be true in the remaining states, and C1 is true in your S3 and S6. Since it is true in S3 and S6, necessarily these two states are going to come. So, T1 implies AFC1 will be true in your S0, S2, S3, because S0, S2, S3, S0, S2 and S5, S0, S2 and S5 in this particular three set, not of T1 is true. Okay, not of T1 is. So, due to this component, these three states are coming, and AFC1 is true in other two states, your S3 and S6. So, these are coming due to this reason. On the other hand, not of T1 is also true over here. So, we are going to get this. But the remaining three states S1, S4 and S7, in this particular three state AFC1 is not true, and similarly not of T1 is also not true, because T1 is true in this particular state. So, these three states are not coming into picture. So, T1 implies AFC1 is basically true in S0, S2, S3, S5 and S6. So, what is not of these things? Already I have said that if phi is true in some state, then not of phi will be true in the total state space minus the set of state where phi is true. Since this particular formula is true in S0, S2, S3, S5 and S6. So, not of T1 implies AFC1 will be true in S1, S4, S7. These are the three states S1, S4, S7. Okay. Now, we have seen the labeling of this particular sub formula along with the negation of this particular sub formula. So, what is my next sub formula? That E true until not of T1 implies AFC1. Okay. Now, we are going to check for this particular thing. So, what is the procedure for E until operator? So, if any state S is labeled with Q, then label it with E P until Q. Again, as per our semantic, future includes the present behavior. Okay. So, wherever Q is true, we are going to label it with E P until Q. Then, we are going to repeat this particular procedure until there is no sense. What is the procedure? Label any state with E P until Q if it is labeled with P and at least one of its successor is labeled with E P until Q. So, first we are going to collect the state where Q is true, we label these things with E P until Q. Then we are going to traverse the entire state space and we are going to check if the P is true in that particular state and one of its successor is labeled with E P until Q, and until there is no sense, that means we cannot collect any more states. If we cannot collect any more states, then we are going to terminate our procedure over there. Okay. Now, in this particular case, we know not of T 1 implies A F C 1. Okay. We know these are the what are the states. It is true in S 1, S 4 and S 7. For E true until not of T 1 implies A F C 1, this will be true in your S 1, S 4 and S 7. As per our first step, if any state S is labeled with Q, then label with it E P until Q. So, from this particular step, what we are getting, that this particular formula will be true in S 1, S 4 and S 7, because this not of T 1 implies A F C 1 is true in S 1, S 4 and S 7. So, these are the initial state we are collecting. Now, from this particular state, we are going to traverse the state space. Okay. Now, next time what will happen? Now, when we are going to look into your S 1, then we will see one of its predecessor is your S 0. Okay. Now, S 0 is labeled with true. No, we have seen that it is labeled, because all the states are labeled with true. So, true until something. So, if it is labeled with true and one of its successor is labeled with this particular your E until your these things, because already we have got these are the 3 states. So, now we are going to include this particular S 0 in the set. Okay. So, it is not having any other predecessor, then we will go to S 4. From S 4 again we will see what are the predecessor. It is having one predecessor and this predecessor is also labeled with true, and now since true is it is labeled with true and one of its successor is labeled with already your this particular sub formula. So, S 2 will also come into this particular step. Similarly, and now it is not having any other predecessor, then we will go to S 7. Now, from S 7 we are going to see what are the predecessor it is having. It is having, of course, from S 4 we are having S 1 also, but it is already labeled. So, from S 7 we are having 2 predecessor S 5 and S 4. So, S 4 is already labeled. Now, in S 5 we will see that it is already labeled with true and there exists at least one successor which is labeled with your this particular given formula A F your these things not of T 1 until E F C 1, that means it is labeled with this particular given formula. So, S 5 will also come into this particular scenario. So, in this iteration we have seen the predecessor of all these 3 states and we are including this. So, this time we are getting a bigger set. So, there is a sense of my set of states. So, again we are going to repeat this particular loop. So, next time what will happen? Now, already we have seen these 3 things. Now, we are going to see S 0. Now, when we are having S 0, then you just see that what is the predecessor that we have. So, we have this particular predecessor because we are having a transition from your S 3 and we are having a transition from S 5. So, S 5 is already labeled. Okay. Now, we are going to see that S 3. Now, again as per our definition it is labeled with true and it is having 2 successor, but one of the successors is labeled with your that particular formula, because already in the previous step we have labeled it. So, your S 0 will come into this particular set. Okay. So, S 0 is S 0 is already included. So, S 3 will also be included in this particular set. Okay. Now, after that already S 5 is there. So, we we already have included it. So, now we have seen that again there is a change in this particular set. So, we will again enter into the loop. So, when we enter into the next loop, then what will happen? Already we have checked those particular state. Now, only S 3 is remaining. So, from S 3 we will see that what is this particular successor S 6. Now, again in S 6 it is labeled with true. Now, one of these things we are having, these things what you call, it is your S 3 is labeled with your the given formula E true until not of T 1 implies A F C 1. So, S 6 will be included in this particular step, and the second predecessor that we are having. So, we need not to look into it. So, you just see that since there is a sense, again we will go into it. Now, we will find that when we enter into the next step, then all are included over here, because we have seen. So, all the states has been included. So, there will be no sense. So, we are going to get in all those particular states, that means entire state space E true until not of T 1 implies A F C 1 is true. Now, my given formula is negation of this thing, since we are going to have S minus this particular set. So, here since this is nothing but equal to your set, so we are going to get a null set. That means, the given formula is not true in none of these particular states. Okay. So, this is the given, we have looked for the truth values of this particular formula, and this is equivalent to my given formula, and we have found that in none of the states this particular formula is true. That means, our modeling of these things, what will happen, the model that we have, no, it is not satisfying our liveness property. So, if any process tries to enter into the critical section, eventually it may not get a chance to enter into the critical section, okay, because in none of the state this particular given formula is true. So, already we have explained that this is happening because of this particular loop. Okay. So, we are coming from S 1 to S 4, from S 4 to S 7, and from S 7 to again we are going back to S 1, like that. So, we are going to get an infinite path in this particular loop. So, from any states, if you look into other states, for every state we are going to enter into this particular loop. Say if, for example, say if I am in S 5, from S 5 I can come to S 0, from S 0 I can come to S 1, and after once reach into the S 1, then S 1, S 4, S 7 it will remain in this particular loop. So, due to this particular loop, this liveness property is not true in our model. Okay. So, already we have explained these things. Now, we try to apply our model checking algorithm, labeling algorithm. Eventually, I found that it is returning me the null set. That means, in none of the state the given formula is true. Okay. Now, after that, when I said that we are coming up a model, we are trying to check for the property, whether my properties are true in this model or not. We have found that the liveness property is not true. Okay. So, in that particular case, what will happen? Designer is going to revisit the design, he will analyze the design, and he will try to modify the design in such a way that the required property will be satisfied in the new model. So, already we have discussed this in our previous lecture, and we have seen that we can come up with a new model like that, where the one state will be broken into two different states over here. Okay. Now, I am giving you a question that apply the model checking algorithm to label the states with the formula A G T 1 until A F C 1. So, this is the liveness property, already we have checked in my previous model. Now, we apply the same procedure the way I have explained it, and try to check whether this property is true in this particular model or not. So, that means, you have to find out a set of states where this particular formula is true. So, it is similar to my previous explanation, only this particular model is different. We had one simple states over here. Now, I have broken this particular state to two different states. Now, with this approach, now you try to get the equivalent, same equivalent will come, same sub formulas will come here also, because I am giving you the same formulas, only this model is different. Now, you apply the model checking algorithm to label the states with this particular formula. It is a very simple example, simple problem. So, you can try it and just see, get a feeling how the model checking algorithm works over here. So, this is basically same formula. I have already explained that this given formula can be break up into this particular equivalent formula, and these are the sub formulas that we are having. Now, you look for a set of states where those particular sub formulas are true. So, it is similar to the example that I have explained, but here what will happen, you have I have slightly changed the model, so that this property will get satisfied. Okay. You take it as an exercise and do it. Now, what will happen, we have seen that minimum set of operators, we are going to look for E x, A f and E u, and other operators can be explained with the help of these three operators. Now, we will see some method whether we can write some procedure for other operators also or not. So, for that I am going to take say some example of E g and A g, because if I am having E g or A g, we have to write the equivalent formula which involve these three operators, but we will see whether we can write procedure for these two or not. If we can write a procedure for these two, then what will happen? My adequate set of operator may be different, because already I have said that I need one next operator, we need one until operator, and I need either f or g. So, for f I have looking into f. Okay. Now, for g also, now you can say that instead of f I can use g. So, I am going to see the procedure for E g and A g. Okay. So, first we are going to look into E g. Now, what we are going to see that labeling algorithm for E g. So, it is slightly defined where I am going to get it. We will say that what is the first step I am going to do, label all the states with E g p, because I am going to look for the formula E g p. So, when I am coming to this particular formula, we know the labeling of this particular sub formula p. So, in this particular approach, what we are going to do, initially we are going to label all the state with the given formula E g p. So, if now step 2, what we are going to do, if any state S is not labeled with p, delete the label E g p. So, what we are starting, I am given a state space, in all the states I put the label E g p. Okay. Now, after that I am going to check the states where it is labeled not labeled with p, because we know the label of p, no, when I am coming to E g p. So, I am going to remove the label of E g p from those particular states where it is not labeled with p. Okay. Now, in step 3, now what we are going to do, delete the label E g p from any state if none of its successor is labeled with E g p. Now, in next step what we are going to do, we are going to delete the label of E g p from any state, okay, if none of its successor is labeled with E g p. Okay. So, and I am going to repeat this process until there is no change. That means, I am going to remove all the label, and after removing the label, what will happen, some more states will come where that E g p is not true, and like that we will repeat this particular process until there is no change. That means, we cannot remove any more labels. So, this is the procedure that we are going to follow. So, this is slightly different from my earlier approach, this is slightly different approach, but still it is going to work, and I will see what is the differences. Okay. Now, these are the 3 steps we have to follow, and let us see whether it is going to work or not, and with a simple example I am going to explain it. Now, come up with this particular Deka structure or model. It is having the state space S 1, S 2, S 3, S 4, S 5, S 6, S 7, S 7, and initially I am having the label of p. When I am going for E g p, I must have the label of p. So, these are the states where it is labeled with p. So, basically I can say that p is true in the state S 1, S 2, S 6, S 7 and S 8. Okay. So, in the first step, label each state by E g p. So, I am labeling each state with the help of this particular E g p. Now, what is the next step? Next step, it says this, remove the label of E g p from the states where it is not labeled with E g p. So, I have seen that it is p is labeled in this particular states, and it is not labeled in S 5 and S 6. So, S 5 and S 6 is not labeled with your p. So, I am removing the label EGP from these two states S3 and S5. So, this is the state. Now, what we are going to do? Next, I am going to remove the label from the states, remove the label EGP from the states where none of its successor is labeled with EGP. So, in this particular case, we will find that already in the previous case I have removed the label from S3 and S5. Now, if you look into this particular state space, if I come for your say S6, you will find that at least one successor is labeled with EGP. When we come to S8, you will find that one successor is labeled with EGP. When you come to S6, it is labeled one of the successor. From E4 also E6 is labeled, S1 also we are getting one, it is having two successors S3 and S4. So, one of the successors is labeled of EGP, but when we come to S2, it is having only one successor S5 which is not labeled with EGP. So, that means now we are going to remove this EGP from S2. Okay. So, we are removing it. Now, delete the label EGP if none of its successor is labeled with EGP. So, I am removing. Then again I am going to repeat these things and we will find that since we are removing it, now this may be a potential candidate S1. Okay. Now, in this particular S1 what will happen? You just see that from S2 you have removed it, but it is having one successor S4 where it is labeled still labeled with EGP. That means, we cannot remove S1. So, similarly, we cannot remove the label of EGP from any of the states. So, eventually our algorithm stops over here. Okay. So, eventually what we are getting, that set of state where EGP is true. So, we are getting the states like that S1, S4, S6, S7 and S8. These are the states, because you just see that here from S1 at least there exists a part where globally play hold. So, similarly for S4 also, because this is sub part from this particular S1. So, again it will happen. Here also you will see that at least we are getting state one part where P is true in all the states. So, this is the set of states that we are getting over here. Okay. Now, see, we have seen the process for your EGP, and the approach is slightly different than the procedure that we have talked about EU and AF. Okay. We have discussed the algorithm for EU and AF, and now we have seen the procedure for EG also. The approach of EG is slightly different than the approach of EU and AF. Now, what is this difference? You just see that for operator AF and EU, basically we start from nothing. So, we are not considering any steps. So, you can say that initially we are starting from an empty state. Now, we are collecting the states that are labeled with Q. So, in AFQ and E P until Q. So, we know that if a particular state Q is true, then AFQ is true, and in this particular state if Q is true, then EP until Q is true. Okay. So, we are collecting those particular states where Q is true. That means, we are starting with a minimal states. This is the minimal state set of states where this particular formula AFQ and EFQ is true. And after that, we are going to repeat our process. That means, while repeating the process, we are traversing the entire state space and we are collecting more and more states. Okay, we are adding more and more states, and until we are going to repeat this particular procedure till the point where we cannot add any more states. Okay, so, this is the procedure. That means, we are starting from a minimal set and we are trying to collect more and more states, and eventually we will stop at the point where we cannot collect any more state. Okay. So, this is the approach that we have used in case of AF and EG. But in case of AF and EQ, EU, okay, there exists a part until operator. But for the operator EG, that means there exists a part globally something is true or not. So, say globally P is true or not. In this particular case, our approach is like that. We are starting from the entire state space. We are initially thinking that in entire state space this particular formula is true. After that, what will happen? We are trying to remove states from this particular state space by looking into the criteria whether EGP is true over there or not. So, this is you just see that approach is slightly different. We are trying starting from the entire state space and now eliminating states where EGP is not true. So, slightly approach is different. One is we are trying starting from the minimal state, and in the second approach in EGP we are starting from the entire state space and trying to minimize it and going to get the set of states where EGP is true. Okay. Now, after discussing this particular EGP, there exists a path globally P holds or not. Now, I am giving a question to you because already we have seen this particular algorithm. Write the labeling algorithm for the temporal operator AG. That means, in all path globally some formula phi holds or not. I am saying that write the labeling algorithm for the temporal operator AG phi. Okay. Now, already we have discussed about EGP. Now, I am saying that you write a algorithm for this. I think this is a simple one. If you look into it, what is the nature of EGP and AGP? Straight away, I think you can write the procedure for AG phi. Okay. It is very much similar to EG. What we did in EG, you just see that we are starting with the entire state path, label all the state with your EGP. Now, if any state S is not labeled with P, then delete EGP. Okay. Fine. Because you just see that AG and EG. AG is a stronger condition than EG. EG may be true in some state, but AG may be false. But if AG is true in some state, then EG must be true over here, because we are talking about all part and EG we are talking about some part on any part. Okay. So, if AG is true in a particular model, then EG must be true, but if EG is true, AG may not be true. Okay. So, in this particular case, we can say that if P is not labeled, then we are deleting EGP. Since EGP is not true, that means AG, there is no question of having AGP true over there. So, straight away you can use these things. Now, what we are repeating over here? Delete the label EGP from any state if none of its successor is labeled with EGP. Okay. What we are saying that if none of its successor is labeled with this. So, we are considering it is in case of your EG, if none of its successor is labeled with EGP. Now, for AG, I am already telling you it is a stronger condition. So, instead of none of its successor, what we have to say? For any state, if none of its successor is labeled with EGP, we have to say all successor basically. We have to look for all successor, because it is your AG in all part globally and it is a stronger condition than AG. So, you just see that straight away you can say come for your AG. Instead of your none of its successor, you can say that all successor are not labeled with your AGP, then remove this label until this. So, label its state with your AGP. If any of S is not labeled with P, delete AGP from this particular state and delete the label AGP from any state if all successors are not labeled with AGP until there is no set. You just see that since AG is a stronger condition, so from EG we can very well do this. Now, what is the complexity issues of this particular either AG or EG? Already I have said that we have discussed about your infusor and until, and of course, in both the cases we need this particular next step. So, this is basically complexity we have talked about, that it is depends on the length of formula, number of states we are having and the total state space. Okay. So, this now we have seen this is in case of F and if. Now, if you look into AG and EG, though we are starting from the total state space, but again we have to traverse the entire state space. We have to look for each and every state whether any one of its successor or all successor are labeled with EGP or not. So, complexity will remain same for AG and EG also, but whether can you improve this particular complexity? So, can you do in some other way? So, if you look for AG and EG, we may have some other way to look for these two operators. Just we will see one of these particular things. Now, what is the way that we are going to do it? Now, this is slightly different approach. Now, see the algorithm. In step 1, we are saying that restrict the graph to states satisfying P, that is delete all other states and their transition. Now, what we are saying, you are giving me the interstate space. When we are going to look for EGP, that means what will happen? When I come to EGP, that means I know that state space is already labeled by this particular formula P or atomic proportion P. Now, we will take the interstate space and I am going to work with a restricted graph. What we are going to say? That delete the states where P is not true and along with its transition. Okay. So, we are restricting it. So, basically just see that I am going to look into it. Say if I am having a state space like that, okay, just explaining it. Now, say this particular state is not have a label of P, that means we are going to remove these particular states. Then when I am removing these particular states, okay, then what will happen? This transition will remain diagonal. So, we have to remove this particular transition also. Okay. So, initially we are starting with this thing. So, we are going to restrict the graph by deleting the states where P is not true, okay, and along with the transition. So, we are going to restrict the graph with the states where P is true. Now, next step in step 2, what we are going to do? Find the maximal strongly connected component of this restricted graph. So, this is maximal strongly connected component that we are going to find. We are having a procedure to do this thing. So, what is a maximal connected component? These are maximal regions of the state space in which every state is linked with every other state. Basically, maximal strongly connected component, basically consider these are the complete graph, complete subgraphs of my that restricted graph. So, that means from any state we can go to any other state. Of course, it need not be complete, but we are having a path from any states to any other states. Okay. So, this is maximal strongly connected component, it need not be complete. Okay. Now, in step 3, what we are going to do? Use backward breadth first searching on the restricted graph to find any state that can reach an SCC. Now, we are going to follow a backward breadth first search on this particular restricted graph to find any state that can reach an SCC. So, we are identifying the SCC strongly connected component. Okay. Now, from this particular strongly connected component, we use backward breadth first search. Okay. I am going to see whether from any state we can reach this particular state or not. So, if we can reach that, that means from that particular state also it will be true. Okay. Now, just see, come to this particular same example, that this is the state space that we are having. We are having states from S1 to S8 and we are going for EGP. Okay. So, in that particular case what will happen? It is already the state space is labeled with this P. So, these are the space where P is true. Now, what happens? We restrict a graph for the states where P is true. So, in this particular case, if you see, out of those states S5 and S3 are not labeled with P. So, we are going to restrict a graph where P is true. That means, we are going to delete these two particular states. When we are going to delete these two states, then along with that we have to delete all those particular transition which are coming to those particular states and which are going out from these particular states. Okay. So, for that we are going to get this particular restricted graph. Now, see here in all the states are labeled with P, because they will be, these are the states will be candidate for EGP. They are exist apart globally P hold. If any state P is not true, then there is no question of having EGP true at that particular state. So, we are restricting the graph where only P is true. Now, next time what we are going to say that find the strongly connected component, and what is the strongly connected component? It is the maximal region where we can reach each state from any other state. So, if you look into this particular state space, you will going to get this particular portion as a maximal strongly connected component. Now, it is having state S6, S7 and S8. You just see that if I am in S6, then I can go to S7, I can go to S8. If I am in S7, then I can go to S8 and I can even go to S6 also through this particular part. And if I am in your S8, then I can go to S6 and S7. So, you just see that if I am in any state, I can go to any other state. But these things you just see that if you are in S4, then you cannot go to S2. Okay, so that is why S4 will not come into this thing. Secondly, if it is considered S4, from any one of these states I cannot go to S4. So, it will not come into the maximal strongly connected component. So, I am getting this as a maximal strongly connected component. Now, what we are going to do now? We are going to have a backward breadth first search from this particular strongly connected component. And if any states can be reached by this particular backward breadth first search, then we can say that will be your formula EGP will be true. Now, you just see that when we are starting from these things backward breadth first search. So, we can reach your P, and if you go for backward, then I can reach S1. But from here I cannot go for backward breadth first search and I cannot reach this particular S2, because this is a directive. Okay. So, in this way these two states will come into picture. That means, you just see that from your this maximal strongly connected component, we can use backward breadth first search to reach S4 and reach S1, and no more states will come into picture. So, after that whatever we can reach from this particular maximal strongly connected component, those states will be having EGP true, because you just see that now wherever you go, you will find that P is true. Okay, because this is eventually you are coming to this particular strongly connected component, and wherever you go, you will find that everywhere P is true. So, these are the state space where EGP is true. So, similarly, we are getting that EGP will be true S1, S4, S6, S7 and S8. Okay. Now, in this particular case, you just see that what the advantage we are getting over here, whether any advantage we are getting, you just see that what will happen, since we are getting this particular strongly connected component, and along with that the backward breadth first search, we are having algorithm which can be done in linear time, which is proportional to the my state space, number of vertices and number of edges. Okay. So, we are having algorithm for your backward breadth first search and finding strongly connected component which works in the order of your V plus E. Okay. So, that is why if we are having algorithm which works in order V plus E. So, that means, in this particular case the model checking algorithm that we are getting, the time complexity will be, it is depends on the length of the formula and your size of your state space or size of my graph. Okay. This is some sort of a graph traversal algorithm. So, eventually the complexity will turn up to be like that. So, for EGP, what complexity you are getting, it is linear on the length of the formula and it is linear on the size of my graph. But in case of your EU and your AF, the complexity is basically linear in the length of the formula, but it is quadratic in the size of my state space, or it is quadratic in the number of nodes that we have in my state space. Okay. So, that means, if you say that instead of AF, because AU I cannot avoid, EU I cannot avoid, because AU I cannot avoid because I can say that EU I cannot avoid because I am having the operator AU have to be expressed with the help of EU. Okay. Now, I have this AF, okay, but we are having equivalence. So, instead of AF, either I can go for EG, okay, because we know that we are having equivalence. So, we can look for one complete set of operator E x, E u and A f. This is one operator set. Another operator I can say E x, E u and say E g. Okay. Now, we can look for A x also, it is similar. So, if we are going to have these things, or I can set it for better, I can set it, it may be A x also. So, if I am going to look for these three operators, then what will happen? The complexity, time complexity will be slightly less. And if we are going to look for these three sets, then the time complexity will be slightly more, because it is quadratic in the size of my graph, but here we are getting linear over here. So, this way either we can go for this particular procedure, or I can go for this particular set of states also. So, basically we are going to look for three set of operators, and others will be expressed with the help of these three operators. So, this is the another approach we have seen, and we have seen that time complexity may be slightly reduced in this particular case. Okay. With this I will stop here today. In next class we may look for some examples where we are going to make model and going to see what are the property it needs to be satisfied and apply the model checking algorithm to do it.